Welcome to this edition of AMD Inside Track. Today we have Juan Flores of the SimNow team. So Juan, could you start by telling us what SimNow is?
Sure. Well, in a nutshell, SimNow is a fast and configurable x86 and x86-64 functional simulator. With SimNow, you can connect together arbitrarily complex software models to form a complete PC platform emulation environment. The platforms that you simulate in SimNow can range in complexity from something very simple to, say, a mobile platform, to something a bit more complex, moving into the desktop or workstation platform, going all the way into extremely complex server configurations that have multiple sockets with multiple I/O bridges.
I understand that you have a demo for us today. Can you give us some background information about it and what you're going to present?
Sure. So one of the main usage models for SimNow is to provide developers an environment that they can test and debug their next generation software that's targeted for next generation hardware before that hardware is actually available to them. So by allowing them to get that test and debug cycle out of the way, they're actually reducing their time to market, and when the actual silicon arrives, or when they get their actual platform that they're targeting their software for, they can finish the rest of their optimizations and timings that the simulation environment was not able to provide.
Okay, what specifically will you be demoing?
So in today's demo, I'm going to be running a small piece of the industry standard SPEC CPU benchmark. The piece of the benchmark that I'm going to be running today has been recompiled and optimized to take advantage of AMD's next generation instruction set architectures, specifically utilizing the AVX and FMA4 instruction sets. AVX stands for the Advanced Vector Extensions instructions, and FMA4 is a fused, multiply, and add with 4 operand instruction set format.
All right, well, take it away.
Okay, so I've got a Linux terminal open here, and what I'm going to go ahead and do is I'm going to go ahead and launch the simulator here. And so I'm going to launch the SimNow with a couple of arguments here. The only one we really need to pay attention to is the last argument here, which is specifying a BSD checkpoint, which is basically a save state of the platform that was being simulated in SimNow. And what this will do, this will allow us to immediately get into an environment where we're ready to run our benchmark without actually having to boot up the OS and wait the 10 minutes or so that it takes for the OS to boot up here. So I've got the simulator open here, and what I'm going to do here is kind of just walk you through the environment first. First thing I'll do is go ahead and start the simulator from the checkpoint. So now we're rolling here. We can go ahead and see the simulated seconds start ticking by here, and this is the host seconds. And then the SimNow's video window pretty much behaves as a normal computer screen that you're typically used to working with here. So from here, I can go ahead and issue commands to the OS that's running underneath the simulator here. So before I jump right into running the benchmark and where we can actually see the instructions being executed, I'm going to take time here to take a look at our SimNow debugger here. And here I want to demonstrate a couple of things that's unique to our model here in terms of its CPU ID bits. So in the SimNow debugger here, I'm going to go ahead and run a CPU ID instruction. I'm going to tell it to fetch the data for CPU ID function 1. Okay? And what we're looking for here is we're looking for the AVX feature enable bit. And this bit will actually tell the software that this processor supports the AVX instruction set. And so the AVX CPU ID bit is found in the ECX register bit 28. So bit 28 would be this high nibble here, and we can see that bit 28 is set to a 1 there. So not only do we know that this processor supports the AVX instruction set, but we also know that the software running inside of SimNow knows that the processor supports AVX. Similarly, with we want to check for support for the FMA4 instruction set. So in order to get that information, I will again execute a CPU ID operation, this time with a different function number. Now, in this function, what we're looking for is bit 16 of the ECX register. So bit 16, here is our nibble that contains bit 16, the one with the value of 5. And so bit 16 would be the first bit, and that is set to 1 there since we have a value of 5. So we know that the processor that we're running here in this simulation supports the AVX and the FMA4 instruction set. With that, I'll go ahead and continue running the benchmark. Let me resume the simulation here. And now I'm going to do a few commands that are specific to the benchmark to actually kickstart things here. Now, what we're running here is actually a piece of the benchmark that actually is simulating, I believe, some blast waves. That's the last argument that I gave to it, the B waves there. And this is meant to represent a real-world environment where we're actually doing some floating point and integer operations that can actually take advantage of these new instruction sets here. So it's going to take a few seconds here for the benchmark to kick off here. Right now, all it's doing is just some preliminary work, and the real meat of the workload should begin in a few minutes. So the benchmark has been running here now, and what I'm going to do is I'm going to go ahead and actually look at what's being executed inside the simulator here. And this is, again, the SimNow debugger. And what we can see here is we can see the current instruction pointer here highlighted in red. And we can see that we're in the middle of some AVX operations here. All the AVX instructions here are, the mnemonic is prefixed with a V here. And if you're familiar with the SSE and SSE2 instruction set, the MoveSD and the SubSD mnemonic should be familiar to you. The AVX instruction introduces the V prefix, which is part of the AVX feature set, which does a couple of things. One, it extends the XMM registers from 128 bits to 256 bits. The upper half of the upper 128 bits of the XMM registers is actually part of the YMM registers. The YMM registers are broken up into two sets: the upper half and the lower half, which aliases to the legacy XMM registers. So we have several operations here that are occurring here. So I'll just kind of go ahead and single step in our debugger here using the trace command. And we can see that the instruction pointer moves as we continue to trace and as we continue to execute more AVX operations here. Now, here's an AVX instruction set that operates with 3 operands, which is another feature set of the AVX instruction set where it supports non-destructive source operands so that the source operands that are used as part of the operation remain unmodified and the destination is put explicitly in another register or memory location. So all of these AVX instructions here that we see have a particular byte encoding. Now this byte encoding, if we were to run it on older generation of AMD hardware, these encodings would appear as gibberish, and our CPU models would actually be generating invalid opcode faults. And so this kind of showcases how software developers can write next generation code and run it in a simulation environment that showcases next generation hardware without the hardware actually being available.